Guys, if possible, if you can please open your cameras, that will be more interactive. So sorry, sir, for keeping you waiting, sir. But still participants are joining. I will, sir, 2 minutes more, sir, please, sir. Guys, please ask your friends to join as we will be very soon starting our event. Please ask your friends to join, ACM members to join. We'll be starting at 7:10. Please ask your friends to join. So, hello everyone. I welcome you all to the interactive session of ACM RGIPT. So actually, this ACM RGIPT is very new chapter which has been I think it's 3 or 4 months only it has been inaugurated. Uh, it's a very I think in RGIPT campus it's a very most growthful chapter in RGIPT campus I think from till now. Guys, please ask your friends to join. We are going shortly, very soon, going to start our session. Sir, hello everyone. I welcome you all on behalf of ACM RGIPT student chapter. I am Mihir Kumar, event coordinator of ACM RGIPT, and today I'll be hosting the event and webinar on hands-on session of quantum computing. On this special occasion, we feel immense honor to welcome our guest speaker, Mr. Sabyasachi Mukhopadhyay, who is an expert in his field. Mr. Sabyasachi is a Google developer and an expert in machine learning, and also he's a TEDx speaker. Well, this perfect blend of qualifications and abilities are beyond match. So I want each and every participant to take out most of him. So let's hear from the experts itself. So, sir, mic is over to you, sir.
Thank you very much. I hope I am audible to all of you. So thanks to ACM chapter of RGIPT, Govt of India for inviting me. It's been a pleasure to be here. So today's topic is all about to discuss on quantum computing. So from your organizers, I come to know there are most of the students from first and second year of B.Tech studies. So basically, this will be a very preliminary basic level of talk and hands-on session. So in the from the upcoming days, we can go for some advanced level topic as well. So this topic is itself an advanced topic in terms of our Indian curriculum, but still I am trying to keep it as lucid as possible because most of the students are from the first and second year of their undergraduate study. So first of all, I would request to all of you to please open Google Colab through Google search. Okay, first search typing on Google Colab. Okay, let me share the screen as well. Can you start? Okay, search it. This link. Welcome to Collaboratory. Okay, and there you click on new notebook. So you see the notebook is opening gradually. So once the notebook has opened, you see there is an option untitled art. There is a naming is given there untitled art. Untitled 8.ipynb. So ipynb stands for interactive Python notebook. So what you do, you click on and edit it. You can give the name QC stands for quantum computing practice. You may give like that. QC practice IPYNB. Okay. And once you are coming to the bottom side, you see there are two options are given: plus text and plus code. So plus text you can click on and keep on adding some text material there. And plus code you can add up some coding. Okay, coding part you can add up there and you can click on the run cell button. It will run automatically. Okay. So I am just going back to my main notebook. So this notebook is for the design for the have been designed for the today's discussion purpose, which I will share with all of you via organizers. Nothing to worry about it. You will get all the details from here. Okay. So let me go back to the first section of today's discussion. So today, as I told you, most of the students are in the first and second year of their undergraduate studies. So our discussion will be very preliminary level because the topic is itself an advanced topic as per Indian curriculum. So today we will go through very basics. In upcoming days, if I get the opportunity, we will go for the much more advanced level discussion. So first of all, we require to understand that why do we require the quantum computers? If you see, for example, the evolution, I want to give idea of some evolutionary way computing has been developed. So basically, in India, the uses of the computers start in the 50s. Okay, and people then used to with the mainframe computers. Okay, quite bulky in size, and concept of the personal computers. Okay, group of people used to share one particular computer, and in the curriculum it was involved in 1963 by IIT Kanpur. They started with the computer science engineering program, undergraduate level, and then gradually followed by other IITs and top universities gradually became inclined toward the computers or computer science related programs. And what happened that in early 70s, it was in our Indian scenario, gradually officers started to explore the computers in order to maintain their databases. So all of you may have heard the term like relation databases, which we basically, there is a tabular-like structure by the help of the row and column-like structure, we basically store certain data. So those were the relation databases, and we have this schema. We call them the schema rigidity factors are there. So these are the relation databases, and mostly data sets are structured data sets. So people started to deal with RDBMS via SQL, structured query language. All of you know that. And then obviously in parallel, if you look after the programming, people are mostly oriented with the procedure oriented programming like C. Then in early 80s and mid 80s, what happened that the Java developed. So via C++, we started to object orientation, and pure object oriented language we came up with Java, and then followed by that in early 90s, by the help of Linux Foundation, they started the GNU Free project. So all the open source era started. Before that, it was mostly on the commercial softwares in terms of the data analysis also. So SPSS, you may hear about the softwares like SPSS, those who are the highly commercial softwares. But open source era started from 1990s, and people started to explore with gradually that started to become quite popular because era, with the help of the open source era, what happens that first of all the software is very freely accessible, and across the board anyone can contribute being the source facility. So what happened that especially that the commercial software, for example, like SPSS, you have to, for example, single user license, it may cost around 1 lakh for one machine. But what happened that if you go with R, Python, that would be quite freely available and accessible. So there's a reason in academic fraternity, especially for the developing countries, it a huge popularity. Now, if we look after the from 1994, we started to explore with internet. Okay, and due to that, gradually we started to use Google and the facilities like Gmail. Okay, and also Mark Zuckerberg came up with Facebook, which is a social media platform. LinkedIn is there, which is a professional social media platform. So whenever we started to typing email, or whenever we started to sharing post in social media, so another type of data set has come up, that is the unstructured data. So whenever you are writing some post, images, videos, those are the unstructured. So in a holistic, why an email, or for example, or doing a post in Facebook or LinkedIn, this is the structured data. So login time, login activity time stored in this. Is getting done day by day, right? So it has an exponential growth.
Sir, your voice is so much lagging, or it's tracking, sir. There might be network issue from your side, sir.
So we got.
Sorry to interrupt you, sir. Hello, sir.
Yes, I can hear you. Can you hear me?
Sir, your voice quality is not, sir, your voice is cracking so much, sir. Sir, if you can turn off your camera, or maybe there is some network issue over there, sir, I think.
Okay, so can you hear me now? Is it easily audible, or is it
So
breaking now?
that time it was breaking so much. I think now it's
But
fine,
but
sir.
but it's fine, right? Okay, so any problem in the audio, just let me know. Okay.
Right, sir. Right. Okay, sir.
So what happened that in general, after that, I mean 2012 onwards. So what I can do, I can stop my camera also, as that we can hear it. But just let me know if the problem persists. I will turn off my camera as well. So in this way, 2012 and 2016, with the help of the GPU and TPU, okay. So deep learning era gradually started. So, but what is the problem is that you see, like I was mentioning, that our digital world has the exponential rate growth. Okay, the every day the digital world is getting double. We have the exponential growth rate. Okay, so due to that our current system not be able to facilitate it. By 25, as according to the experts. So let me stop my video and let me know that whether my voice is clearly audible or not. Is it audible clearly now? Is it clearly audible now? Hello? Thanks for the feedback. To do that, we require some tool which can tackle this abundances. So the point is that in classically what happens that we have two types, right? But in quantum, we don't only have the 0 and 1, but we can generate lot of intermediate bits, qubits, we call qubits, with the help of the super property. Okay, gradually going to discuss that. As you know that by 2035, we must require quantum computers. All classical capabilities which we have to this exponential group of databases, that will be saturated. A lot of investments are being made in terms of quantum research. Government of India nowadays also investing a lot of money in terms of the quantum research. Okay, so you have to have some knowledge about the domain. A lot of people, for example, nowadays are going for the quantum deep learning. Okay, gradually started to getting the quantum. So this required to be accustomed to quantum phenomena more. Notebook. So before quantum, what I am doing, I am just so glimpse of the classical gets first. Okay, because it may happen that those who are from first year do not have much experience. In classical phenomena, what we do, we call them as the binary digit. Okay, either zero, these two gates are possible classically. Now, classically, that one a single, if we are considering the two single bit gates, logic gates, so there are two types of the logic gates. One is the NOT gate. That means whatever the input you will be given, you are giving, that will be inverted, or you can have the identity gate or OR gate. So the input you are giving, the output you are getting. So Google Colab is a platform where you can get all the not only Python but all the Python. Okay, you can run any Python like TensorFlow, Quantum, PyTorch, everything. So this is the first portion of the code. You see, what we are typing. First of all, we are checking the classical identity gate. Okay, so we are defining first function IDTY A. If A is 0, then it will return 0 because it's an identity gate. Whatever the input you will give, according to the output you will get, or else return 1. So according to will print and you will get for the new line, you see, that means output will be printed at new line. So input 0 is 0, output of input 1 is 1. Doing in the copy pasting the code in comment box. Okay, requesting you guys to run the code. Okay, just copy paste comment box, run the code, but make sure that particular lines are maintaining proper synchronization. Follow the screen and make sure that you are maintaining the synchronization of the line properly. Okay, because that indentation error happens in case of the Python if you are not providing proper spacing. Okay, in other programming languages, what happens that indentation will give for the making the code looks much more stylish. But in case of Python, if you are not giving the proper spacing, it may happen that certain error may happen. So identity, this is a slash sign I have given, the hash sign I have given there. So due to this hash sign, this part will not be counted under the code. Okay. Then we are defining the function. Okay, if a equals to 0, return 0, else return 1, and then we are printing the output as per the input. Okay. So if you can run the screen and align your code lines of the code according to that, and let me know if it is running successfully. Click on the run cell button. Okay. Once you are aligned like this, make sure you are preparing the line of the code or arranging the line of the code according to the screen. Okay, I have pasted it in the comment box section. Okay, so is it running? Let me know by commenting on your comment box. Okay, by commenting on your comment box, let me know if it is running. Okay, running. Output for 0 is 0, 1 is 1. Why? Because it's an identity gate. The output you are giving, the input you are giving, as per the output will come up. If you are giving input 0, output will be 0. If you are giving input 1, output will be 1. Because it's an identity gate, you see. You will get this type of output. Output of input 0 is 0, output of 1 is 1. Okay. So I am waiting for a few more responses, then I will move to the next part. Okay. So please let me know if it is running. Already, thank you, Avit Agarwala, for your confirmation. Okay, thank you, Ankita De. Thank you, Sona Saji. Okay, so they all have confirmed that the code is running. Okay, fine. So I will wait for another 1 minute and then I will move to the next part. Okay, so this is the classical identity gate. We are just revising our concept on classical gate because it may happen that during your study we may not have studied at that part of the digital electronics, because these classical gates are the curriculum of the engineering study where you are while studying the digital electronics. Okay, so we are brushing up that part, classical bit part, and they we'll see some performances of the single qubit quantum gates. Okay, we are just brushing up our knowledge on the classical gate, and then we will move to single qubit quantum gate. So these are the demonstration of the single bit classical gate, single bit classical logic gates. Okay, so this part we have done. Now you will see the example of the NOT gate. So in case of NOT gate, what will happen? If you are giving 0, it will be inverted to 1. And if you are giving 1 as an input, the output will be 0. As simple as that, right? So in case of the quantum, in case of the NOT gate, what will happen? Whatever the input you are giving, that will be inverted. Okay, so yes, working. Dipti, thank you very much for your confirmation. Akash Chauhan, thank you very much. Ritika Akula, thank you very much. Okay. Okay, very good. So now we will go to the next part. Okay, now we will see the performance of the NOT gate. So again, I am pasting the code in your issue in a similar fashion. Align the lines and then you, okay. So NOT gate, what we are doing, we are not under that function, we are putting the conditions equals to 0, return 1, because you know, in case of the NOT gate, whatever the input will given, we are giving, that will be. For example, if a equals to 0, return 1, else return. So if under that we can print the output of the NOT gate for input 0. Okay. So if we are giving the input 0, output will be 1. If you are giving the output of the NOT gate is 1, input of the NOT gate is 1, then the output will be 0. So according to that, you will get the outcomes. it will be inverted. Okay, whatever the input we are giving, that will be inverted, right? So if your input is 1, output will be 0. If your input is 0, output will be 1. So according to that, you just align the lines of the code, because as I told you that in Python, it's an indentation error may come up if you are not giving proper spacing. For example, like while defining the function, first line, the next line, when you are going for the condition, it put at least one space. Then again, while writing the line return, you have to give another one space to maintain the, okay, one more round of space. Again, once you come back, else will be in the same indentation, will follow the same indentation line. Okay, in horizontal to if. Then again, whenever we are going to next line, you are putting one more spacing while writing return. Okay, in this way, maintain the indentation. Okay, otherwise indentation error will come up in case of the Python. But one good thing is that in case of Google Colab, whenever you are going to the next line while typing, it sometimes it in generally it will give you the auto positioning of the lines. Okay, that's the benefit of the not get. Sorry, Google Colab. Okay, in other programming languages, indentation is making the coding looks much more. But in case of the not get, in case of Python, what will happen that it is given to get the indentation is given in order to avoid. Okay, so you have to follow the proper indentation, right? So not get, for input 0, output will be 1. For input 1, output will be 0. Hope the code is running for everyone. Okay. Oh yeah, miss it. Function call. Okay, output 0. Okay, thank you. Yeah, A has been specified under the condition. You see, if A is 0, return 1, else 0. Because else return 0. Already it has been defined under the function not. That's the reason it is showing under the print command. Okay, if output of not get for input 0 is 1, output of not get for input 1 is 0. Okay, everything is given there. Otherwise, your output will not come up. Right. Okay, so Mihir Kumar, thank you. Ovik Agarwala, Nitunj, Ashutosh Kumar, thank you very much. Thank you. Look, if any problem is there in the code, they will not give it the output correctly, right? So just follow the coding properly. Functions are first defined, then the explanations are given. But you are defining certain function, under that you have to put the proper conditions. Otherwise, output will not give you the correct result. So according to that, we have defined definition like we have done for the identity gate also. If you see, in identity gate, for input 0, output was 0. For input 1, output was 1. So according to that, we have defined the identity gate, IDTY function. And here also, we are simply, in a similar manner, we are defining the NOT gate, and we are printing the outputs. Okay. Now we will move to next part, that is OR and AND gate. Okay. So in case of the OR gate, what we do, that if both the bits, now we are going for the multi-bit logic gates. Here for NOT and identity gate, we have dealt with only one bit. Okay. Now in case of the OR gate, we are dealing with 2 bit. So for example, the possible scenarios, what can happen? Both the bits are 0, A0, B0, then output will be 0. But rest of the conditions, in case of the OR gate, as per the definition of the OR gate, for rest of the condition, it will display output 1. So for example, 0, 1, A equals to 0, B equals to 1, output will be 1. For example, if A equals to 1, B equals to 0, output will be 1. It may happen that both the bit A and B equals to 1, output will be 1. Okay. So in this fashion, the output will be printed. So that's the reason the logic has been written under the function or function def or AB. If A equals to 0 and B equals to 0, return 0, else return 1. Okay, and then we have defined if name equals to main. Under that we have stated all the print comment. The output of OR gate for input 00 slash n. So in the next line, the output will be printed. Okay. In similar fashion, the output of OR gate for input 01 is again slash n. So in the next line, output will be printed. In a similar fashion, we have done 1-0 combination and 1-1 combination. So once we run the code, you can see this type of output will come up. Output of gate for input is 0. Output of OR gate for input 01 is 1. And output of OR gate for input 10 is 1. And output of OR gate for input 11 is 1. So in this way, you can get the following outputs. Okay, as per the given input. Okay, so make sure that you are running the code correctly. You are putting the positioning the each line of code properly. I am just pasting the code in the comment box section. Okay. So please run that part and let me know if it is giving the output properly. So 00 will be 0, 01 will be 1, 10 will be 1, and 11 will be 1. So let me know once you have run it successfully. Yes, running. Yes, running. Thank you. Thank you. Okay, very good. Very nice, Ankita De. Ashutosh Pradhan, thank you very much. Bhuvik Agarwala, thank you. Thank you. So we have done with the OR gate. Now another two classical bit gate is AND gate. So in the AND gate, what we do? Basically for 00, it will be 0. Otherwise, in every, for example, 010, 100. But in case of 11, it will be 1. So except A and B, both are 1. Otherwise, every cases it will be 0. That means for 000, for 010, for 100, and for 111. So only both the bits are 1, then output will be 1. So in case of the AND gate, you see, once we have def and AB, if A equals to 1 and B return 1, else return 0. So according to that, if we are running the print command, so I am not explaining again. So we have the 0, 0, 1, 10, 11. So once you run the code, you see the output of AND gate for input 00 is 0. Output of AND gate 01 is 0. 010 is 0 and 11 is 1. So I am just pasting the code in your comment box. Okay. Make sure you are running it. Okay. So this is the AND gate. While running the code, make sure that there should not be any indentation error. Okay. Let me know once you have run it successfully. Okay, so thank you, Ali Bhavik Agarwala. Thank you. Thank you, Alik. Thank you, Rupsik. Thank you very much. Thank you. Thank you. Very good. So now we will move to the few more parts of the classical gate just for our revision purpose. We have done with OR, AND gate, NOT gate, identity gate, exclusive OR gate. So exclusive OR gate, we all know what we do in the exclusive OR gate. XOR gate we call. So basically A and B are given. So if both of them are equal, then output will be 0. If both of them are not equal, then output will be 1. So A equals to 0, B equals to 0, output will be 0. A equals to 1, B equals to 1, output will be 1. Output will be 0. And rest of the cases for 0, 1, A equals to 0, B equals to 1, or A equals to 1, B equals to 0. In those cases, output will be 1. So what I am doing, I am just pasting the code here. Just let me know. So for in case of the input 00, output will be 0. For 0, 1, output will be 1. For 0, output will be 1. And for 1, 1, output will be 1. So, in case of the XOR gate, you can see that it's an inequality detector. It's dealing like inequality detector. When both the inputs are not equal, output will be 1. When inputs are equal, in case of both the bits, output will be 0. As simple as like that. So then we will move to NOR gate and NAND gate. These two gates are the universal gate. Okay. So because why we call them universal gate? Because with the help of them, we can construct any other logic gate, right? So the NOR gate, I think it is running for all of you, right? Okay, running, sir. Thank you. Okay. So in case of the NOR gate, what will happen? That if A equals to 0, B equals to 0, output will be 1, or other cases it is 0. Because it is the negation of the OR gate. NOR gate is the negation of the OR gate, right? So in case of OR gate, what was the condition? That if A and B both 0, then the output will be 0. Rest of the condition output will be 1. So if it is a negation of OR gate, NOR gate, so what will happen? Then in both the cases, when A equals to 0, B equals to 0, output will be 1. Rest of the cases, it will be 0. Okay? So what we are doing, we are simply pasting it in your comment box section. Okay? And let me know if you are getting the same type of outcome. So in case of NOR gate, always remember that is a negative. So in all the conditions, it will the negation of the outcome like we are getting from the OR gate. So in case of OR gate, for 0, 0, 0, rest of the condition it was 1. So as the negation of OR gate, that is the NOR gate. So what will happen? In case of both the, whenever you are matching both the gates, for example, 0, 0, it will be 1. And rest of the condition 0, 1, 1, 0, and 1, 1. For rest of the condition, the output will be 0. Okay. So let me know if you are getting the proper outcomes. Okay, very nice. Thank you, Oli. Thank you, Avik. Thank you very much. So I am moving to NAND gate. So NAND gate is the negation of the AND gate. Okay. So in AND gate, what happens that if your A and if your A and B, okay, both are 1, then your output will be 1. That we have seen for the AND gate. So as this is the negation of the AND gate, so what will happen? If A and B both will be 1, the output will be 0, and rest of the cases you will get 1. Okay. So that means for 0, 0, 0, 1, 1, 1, 1, 0 conditions, your output will be 1. And for your conditions like 1, 1, output will be 0, as this is the negation of AND gate. Okay. So in the similar fashion, we have defined the code under the NAND function equals to 1 and B equals to return 0, else 1. Okay. So I am putting it here in the comment box. You just run it and let me know. So this was all about the classical bit purpose, AND gate, OR gate, okay, NOR gate, NAND gate, identity gate. Those who are from the first year participants, they are now benefited from that particular review, that you guys have the idea that what type of the gate outcome you will get while dealing with the classical gates, and you can run the code in Google Colab with simple Python programming. Okay. What is required is all about basic knowledge of functions, how to define a function. Okay, that's it. With that, you can implement it in Python code in Google Colab, right? Okay, running. Okay, thank you, thank you. Now we will move to the linear algebra part, which is the basic necessity for going towards the quantum computation. So we have seen the basics of the classical gates. We have revised it. So basically, what will happen in case of the linear algebra? We will just brush up few of our knowledge on the related to linear algebra. Okay. So for example, how we can define certain vectors. So what we have to do, we have to use module NumPy as NP. So then we can define the arrays. Like the arrays are basically multi-dimensional kind of things. Okay. So if it is one-dimensional, then arrays become vector. If it is two-dimensional, it will become matrix. So in this way, we define the vectors and matrices under the array. Okay. So in NumPy.array, np.array. So whenever, for example, NumPy is the name of the module in Python for the array, for executing the array operation. So import NumPy as NP. NP means alias. Okay. In an abbreviated form of NumPy, we call it as alias. So import NumPy as NP. NP.array, we can define the three components. Okay. 1 equals to NP.array. 4, 5, 6. Okay. Then NP.array, for example, from vector to define, for example, matrix. So how can we write it? So array 1, 2, 3 is the first row elements, 4, 5, 6 in the second row element, 7, 5, 6 in the third row element. Okay. In case of the B, whenever you are defining B, np.array, it is also another 3 cos 3 matrix. So you can define in the first row, for example, 2, 3, 4, 1, 2, 0 in the second row. Okay, 3, 3, 3 in the third row. In this way, we can define vector matrix. Okay. We can also do the tensor product and matrix. So whenever you are doing the tensor, how you can do it? V equals to np.kron. Kron function you can use. X comma W equals to np.kron y b. Okay. So the tensor product of y and matrix B can be defined. Okay. We can also execute operations like in the linear algebra, which is a very, very preliminary thing, whether you are exploring quantum domain or even in case of data science also, it is a very, very important thing to have idea about the vector matrix, how to calculate eigenvalue, eigenvectors. Those things are there. Okay, so for example, vector addition, z equals to x plus y, z equals to x minus y, vector subtraction. We can do the scalar multiplication as well. Z equals to 2 into z. This is a scalar multiplication. Okay, you can do the matrix multiplication. Okay, so those kind of things you can explore. Okay, tensor addition, tensor multiplication. So these are some parts. Okay, I have just highlighted this portion just to give you some idea that what type of operations of the linear algebra operations we can execute in Google Colab or by utilizing the Python. Okay. Now, for example, what we will do, we will see some of the simple examples of the linear algebra. For example, we want to do the dot product. Okay. So import NumPy as NP. So first vector is with 3 elements. Okay. NP.array. So in the x and y we have defined. Then what we are doing whenever we are doing the dot product inner. Okay. So in that case, so element to element wise multiplication addition will happen and you will get the output 32. Okay. So np.inner you have to do, and which will be the output will be assigned to A, and you are simply printing A. So you will get the output 32. To run the code, which is posted in the question, and let me know. Import NumPy as NP, x equals to np.array 1, 2, 3, and y equals to np.array 4, 5, 6. Execute NumPy.inner. Okay. Output is stored in A, and once you print A, you will get the output 32. So this is the part of product, vector inner product. So this concept should be very, very clear. What is inner product? What is outer product? Okay. Because as I told you that linear algebra is the one of the preliminary thing which you require to know while jumping into the quantum computation, because there will be concept like unitary matrix. Okay. So those, to understand those concepts, you require to know this type of stuffs. So let me know once you are executing it successfully. Yes, Google Colab supports all the open source libraries, any Pythonic platform can be run in Google Colab. Okay, any Pythonic platform. So thank you very much, all the participants, those who have acknowledged that running. Okay. Now we are going to the vector outer product. So in case of the outer product, import numpy as np equals to np.array 1, 2, 3, y equals to np.4, 5, 6. Now np.outer is the function to execute the outer operations operation in Python. So those things explored in your first year of study or in the part of your first semester study. In case of while studying linear algebra in your classroom, you have executed theoretically, you have calculated all those things. Those things you can easily do by using Python. Okay. So I am just pasting the code in your comment box. I can see your comments are coming up, some queries are there, so I will gradually address all those comments at the final during the Q&A session of our discussion. So feel free to ask me the questions then. Okay. So import numpy as np.array 1, 2, 3, 4, 5, 6, and then you are doing the outer product and you are getting the outer product operation. In earlier case, we have done the inner product operation. Here we are doing the outer product operation. So once you have run it successfully, just let me know. Okay, very good. You are getting the correct outcome. Very nice, very nice. Thank you. So we are done with inner product and outer product. Now we will see the determinant. Okay. So one of the property of the matrix is determinant. So determinant of matrix are defined by using the square matrices. Okay. So where the number of rows and columns are same. Okay. So determinant in generally we write in det of A. Okay. So basically, whenever you are running the Python code, first of all define the numpy array and np.linalg. Okay, np.numpy.linalg is used for the linear algebra, and then you are putting det a function or extension of the and then you are printing the determinant. Okay, so you will get 24 point something as an outcome. So always remember the function we use np dot lin alg dot det, and under that you can write the numpy array name. If it is A or B, according to that will be given and it will be printed the outcome. Okay. So I am pasting the code in your comment box section. Just let me know once you are able to run it successfully. Okay, very nice. So all of you are getting the correct outcome. Thank you. Thank you for your acknowledgement. Now we will see the transpose. So transpose, what will happen? Flipping of the row and column. Okay. So we are seeing the matrix transpose is shown there in the Python code. So importing numpy as np as the common step. Then we are defining 3 cross 3 matrix. And then we are calculating the determinant and we are simply taking the np dot transpose, numpy dot transpose. Okay. As simple as that. Run it and let me know. Okay, very nice. Okay, thank you. Thank you very much for your acknowledgement. So that's the basics of the matrix. Now we will see understanding the of tensor product. We are gradually moving towards understanding of the tensor product is important. So tensor product, what is the concept of tensor? I was mentioning that's a generalization of a vector or in the higher dimension. Okay, there is no limit of dimension while discussing. The purposes of this session that we are basically interested in two properties of the tensor. Okay, one is the trace of a tensor product, and then one is the partial trace of a tensor product. So in generally, tensor is defined like, okay, so T equals to A tensor B. Okay, so we can do modules. We are extra one extra module we are using here, that is the Qtip module. Okay, so pip install Qtip we will do, and then from Qtip we will import asterisk. We are putting asterisk sign because we are accessing all the libraries under the module. Modules are nothing but the collection of libraries. So under that module, whatever the libraries, whatever the functions are there, everything is accessed. Whenever we are accessing everything, we in general we are not defining a particular case. We are just putting the asterisk sign. So from Qtip import asterisk, then import numpy as np. Then what we are doing, we are basically A and B under these two we have defined. Then what we are doing, we are converting it to the Qtip object, because you see Python, everything is under. This is also an object language. Everything is object. So Qtip object A and Qtip object B. Then what we are doing, we are computing the tensor product using Qtip. Okay, I have given two examples. You can either do it using the tensor product simply using tensor function. So it will be assigned under C. So to tensor A, then what we are doing, the operation using the number. First operation you are doing using the Qtip module, using the, okay. So D equals to np dot caron AB and print D. So you can see the same type of output will come up. Okay. So you see under the QOBJ data, okay, whenever you are getting the tensor product of C, 4, 8, 16, 12, 6, 12, in this way it is printing. It is not taking the floating or imaginary part. It is only output is the part, okay. Output, whenever the Qtip module, you are using the Qtip module and you are printing that using the tensor function, is only 4, 8, 6, 12 in this manner, it is coming. But whenever you are using np numpy dot caron function, okay, under the the tensor operation, okay, you are getting the output with real and imaginary part. Although the imaginary part is 0, but it is writing, whenever you write the complex number, you are writing like A plus IB format. In programming Python, what it write? A plus BJ format, okay. So A is there, real part is there, imaginary 0. So it is A plus 0J format. Okay, that's we are running through online. Okay, we are running through online. So pip install Qt, and then from import numpy as np. Okay, we find A and B arrays and the arrays into the objects. What we have calculated details. So then we have calculated utilizing but if we function from use the real part as an output. Function the module, your image the output like plus 0.
Sir, sorry to interrupt you, sir. Again, your voice is too much breaking, sir.
Yes, yes.
So I think there is some network issue. That's why. Hello. Hello, sir. Can you hear me? Hello. Hello, sir. Can you hear me? So actually, your voice is not coming. Hello, sir. You're not audible, sir. Guys, I think sir is having some network issues on his side. Please wait for a minute. We are contacting him. We are contacting sir. Please wait for a minute. So sir is checking the connections. He will be here within a minute. There is some network issues on his side. Please hold on, guys.
Hello.
Yes, sir. You are audible, sir. Now, yes, sir. You are audible, sir. Guys, please hold. Sir is having some serious network issues over there. We are contacting sir. Hello, sir. You are unmuted, sir. So if you can hear me. Yes.
Can you hear
Yes.
me?
Yes, sir. Now we can hear you clearly.
Okay, excellent. So, okay. So give me the permission to share the content. Please enable the content for sharing. Can you see the screen? Can you see the screen? Hello. Hello.
Yes, sir. We can see, sir.
Okay. 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 Nice. So that is how we have seen that this part is done. Okay. Now we'll move to the next part. So these are the very few basics of the trace and partial trace are given there. And I am not going for the theoretical explanation because we are running short in time. So from your any standard, linear algebra notebook, you can see that how the tensor products are done and what is the concept of stress and partial stress. Okay. Rather, I am mostly relying on the coding part because we are running late. So basically, just to mention that if you are doing the trace, for example, uh, if you are a trace of a tensor can be considered as the, for example, if you are taking the TR function, so TR of T will be equal to TR of A into TR of B, and if it is a partial trace, so that means you can so for example, A trace of BT will be trace of B into with the tensor operation of AB, so it will be A into trace of B. Okay, and B equals to in a similar fashion trace of A of T. So T is assigned to the tensor product of A and B. So trace of A is operated over tensor product of A and B, and at the outcome you will get B into trace of A. So this is how the partial trace concept is. Now, for example, we want to check the trace and partial trace, both the operation you want to explore through the following code blocks. So in a similar fashion, from Qt import asterisk, and then that means all the all the libraries you are installing it. Then from import numpy as np, and then you are defining two numpy as a and b, and you are redefining it with the qt object by using the function of qabj. Okay, qabj function over a and b, and then we are defining the tensor a and b and assigning them as under the name of the t. Okay, and then we are printing tensor product t. Okay, and then we are also printing trace of C is T dot R function. Okay, and also we are putting them, for example, whenever we are calculating the trace, so TR underscore B, we are writing T dot pitch trace. okay, over 0. Okay, and another one is tr underscore a. We are putting the partial trace operation p dot trace over 1. Okay, and we are printing both of the cases, print tr underscore b and print tr underscore a. So this type of output you will get once you do that. Okay, your tensor product result, your trace result, and your partial trace result. Okay, this 4 type of outcome you will be able to see. I'm just requesting it in your comment box window. Okay, just make sure that you can run it. Okay, so I have pasted the code in your comment box window. Let me know if you can run it successfully. You will get the 4 type of outcome. One is the result for the tensor product, another one is for trace, another 2 for the partial traces. Okay, just let me know. Those who already have Qtip imported, you don't require to import it again. Those who have not imported Qtip, it will show error that your Qtip has not imported. So those who have the Qtip imported, you will get the correct output. Okay, and those who do not have the imported Qtip, that may show some. Okay, so are you getting the output? I'm just sharing the screen. You just check it. You will get the following type of output. See, this type of output you will get. Once you are able to run it successfully, this type of output you will get. One for QOBJ data, okay, where you will get the tensor product result. Then trace of C is 21.0. Then trace underscore B, which is the partial trace result, and again under the tr underscore A will give you the partial partial trace result upon A and partial trace result upon B. These two you will get here. So this type of outcome you will get. Let me know once you are being able to get this type of thing. Those who have not imported Qtip, you have to import it. If it is in Colab, you can type exclamatory sign and then keep install Qtip. And those who are running it by installing the software in your machine, you just simply type keep install. You don't have to give the exclamatory sign before that. Keep install Qtip. Okay. Are you getting the output? Let me know. So it is 8:11. So I will wait for another 1 more minute, and then I move to next topic. So those who are running fine, those who are facing difficulty, okay. So just let me know. We will move to the next portion. So I think a few of them already has got the correct outcome. Okay. These notebook will be given to share with the organizers. They will share with all the participants. Okay. So nothing to worry about it. So just try to follow the steps. Okay. I am sharing it in your comment box. If you are able to run it successfully, that's fine. In case if you are facing some difficulty in importing Qtip, you may try later on. Because we are running late. So now we can see that under the qubit operations, because we have already seen the operations of the classical bits, we have seen the very basics of the linear algebra, and how to do the vector multiplication, matrix, vector multiplication. We have learned the concept of the tensor traces, partial traces. Now we will see the qubit operations. So qubit are basically the quantum bits. Okay, here it will not limited to 2 types of bits, 0 and 1. You can go with other intermediate bits by using the superposition property of it. Okay, so the there are many classes of the qubit, quantum gates by utilizing qubit. There are many classes of the quantum operations which you can execute through quantum gates. So the first class of the quantum operation is the unitary gates, which we are discussing today basically. Unitary class. So those quantum gates are reversible by nature. In case of the classical gates are not reversible by nature, but quantum gates with the unitary class, they are reversible by nature. But another gates are there which are the measurement gates. Okay, so when you will go to some more advanced level, then you will come to know about the measurement gates. So those are irreversible in nature. Okay, so since the measurement is irreversible in nature, so you cannot recover the initial states. Reversible means you can recover the initial states. If it is irreversible in nature, you will not be able to recover the initial states. So there are differences. Okay, so the measurement will force the qubits to collapse on either of the states, 0. So in case of the Pauli gate, today's topic is all about exploring single quantum gates, single qubit quantum gates. So under that, Pauli gates plays a very, very important in case of the single qubit quantum gates. So the whole concept relying on the linear algebra. That's the reason I given some demonstration on the linear algebra part in Python. So if there will be the Pauli matrices, which are very commonly used in quantum gates. So there are 2 cross 2 unitary matrices. Okay, so unitary matrices are denoted with capital U. Okay, so this is nothing but a square matrix. So what is happened that if you have this square matrix of n cross n, okay, then we can call that unitary operator. We can apply an unitary operator by utilizing single qubit. Okay, and in some examples of the Pauli gates, can be, for example, X gate, Y gate, Z gate. Okay, so in X gate, in the format of the Pauli representation, if we see this type of format, you can see X gate equals to 0, 1, 1, 0. In first row, it is 0, 1, second row, 1, 0. Okay, and it can be represented with 0 gate 1 bra plus 1 gate 0 bra. In this way, you write it. Okay. So, for example, if you are affecting, if you are applying the X gate over 0 gate, you can see in the following example after doing this basic demonstration on the X gate, formation of the X gate, you are applying the X gate over 0 gate. Now, once you are applying X gate over 0 gate, what is the format of the X gate? 0, 1, 1, 0. And a 0 gate means what? It will be a column vector comprising of 1, 0. Okay, 0 gate means column vector comprising of 1, 0. And if you are multiplying them, you will get a column vector comprising of 0, 1. So 0, 1 means 1 gate. So what is happening that you are applying the X gate, which makes the amplitude switch from state to state 1. It is switching the amplitude from 0 state to state 1. That means X gate is operating like a NOT gate. X gate is operating like a NOT gate. Okay. So you can see there is a rotation by pi radian on the Bloch sphere. Okay. It is a rotation by pi radian over the Bloch sphere. Over the Bloch sphere, you can define the Pauli gates. X, Y, Z, 3 types of the gates are there. So it's a rotation over the Bloch sphere where X gate is acting like a NOT gate. Okay. So before going to Y and Z gate, let's give a demonstration of the X gate. So first of all, as usual, pip install Qtip will be the first step. Then from Qtip import hashtag, that means all the necessary libraries under the Qtip module we are installing, and then importing NumPy as NP. Then what we are doing, A equals to NumPy array np.array 10. Okay, that means we are first entry we are giving 0 gate under A, and second entry B np.array 0 and 1. That means 1 gate under B. And then what we are doing, we are putting sigmax function for X gate for Pauli matrices under Qtip module. We can explore sigmax function, okay, which is defined as row X. Okay, now what we are doing as usual, we are converting object A and B under the Qtip object. Okay, so QOBJ function has been applied. Then what we are doing was simply multiplying, we are simply applying x gate over a gate 0, and then we are assigning the result under C, and we are applying row underscore x. That means x gate. Row underscore x is the playing the role of x gate. X gate over B. B means one gate. Okay, with the entry of 0 and 1 column vector. Then we are printing C and D. So once you run it, you will be able to see following outcome. You see the outputs are inverted because we have seen the X gate is playing the role of NOT gate. Okay, so outputs are inverted. You see, we have given 1 0. That means 0 gate as the entry of A. Now it has been inverted 0 1. That means 1 gate. You are getting the output 1 gate. There you see, we have given the input 0 1. Okay, we are getting the output 1 0. That means 0 gate. So 1 gate and 0 gate, the output has been inverted. So this is how you can see that X gate is playing the role of NOT gate. The explanation is given there, like I was mentioning. At the first step, we have used the modules of the Qt and NumPy. Then two vectors are created using array function. A new variable we have assigned row x, which is playing the role of x gate by using sigma x function from Qt module, and then C and D are assigned as the product with the row x and A and row x and B. Okay, and this C is equivalent to applying x gate over A. So the bits are flipped. That means 1 0 becomes 0 1. If it is 0 1, it will become 1 0. So 0 gate will be converted to 1 gate, and 1 gate will be converted to 0 gate. So in this way, you can see that X gate can perform this type of operation in quantum domain, which is a good example of the single qubit quantum gate. Okay, I am pasting the code in your comment box section. Let me know once you are able to run it successfully. Okay. Just let me know once you are able to run it successfully. We'll move to the next part. Okay. So this is the efficacy of quantum X in quantum domain, the efficacy of X gate. Let me know once you are able to run it. And do not worry, every explanations are given in the notebook. So once I share it, you will get every details out there. So I think we require to do some more sessions on quantum, so we can cover much more advanced topic on that. Today we are doing it at a very basic level. So all the basics have been brushed off first, and then we move there. Okay, so people are getting correct output. Thank you very much. So make sure that your foundations are very strong. You are understanding the linear algebra very well. You have very strong foundations in quantum mechanics. You have a very good understanding of the classical bits, digital electronics, basic gates, at least the basic gates portion of the digital electronics. So it will be easier for you to explore in quantum domain. You can make the parallel tally, how the qubits are performing, what are the shortcomings of classical bits. Okay, because you know that in some complicated operations which we can do in quantum computers within few seconds, which may take several years for the multiple multiple classical computers. Okay, so one quantum computer is equivalent to, in some cases, it can be up to 5 million classical computers in terms of the speed and efficiency. Okay, so that's the reason we are going forward towards the quantum domain. Okay, so I think I can see that people are running it correctly. So I am moving to the next part. So basically, we have done with the X gate. Now Y and Z gate, you can see that Y gate is defined as 0 minus I0. Okay, so it can be written in general information. Minus I 0 gate plus I 1 sorry, minus I 0 gate 1 bra plus I 0 1 gate 0 bra, and in case of the Z gate, the entries are 1 0 0 minus 1. So Z gate basically generalization, you can get 0 gate 0 bra minus 1 gate 1 bra. So we will see the further explanation in below. After the X gate, we will talk about the Z gate. So in case of the Z gate, what is happening in single qubit Z gate? Z gate leaves the 0 gate unchanged, but it will make the sign of, it will make the change in the sign of 1 gate. Okay, so if you are applying 0 Z gate over 0 gate, you will get the output 0. But if you are applying Z gate over 1 gate, the output will be minus 1. means once Z gates are applied over 0 gate, nothing change will happen. But if it is applied over 1, it will become -1. Okay. So, for example, if you see the code here, in a similar fashion, we are installing Qt, then we are putting from Qt import asterisk. That means all the necessary libraries are being imported. Import numpy as np. Then you are writing a equals to in numpy.array 10 and b equals to np.array 01. Okay. And then what you are doing, you are assigning row underscore z under the sigma z function. So sigma z function is available under the library, under the module of YouTube. Okay. So what will happen? It will help you to execute all the gate related studies. Okay. Then you are assigning A equals to QOBJ and B equals to QOBJ. That means you are converting using QOBJ function, using the QOBJ function, them under the QQ object. Then you are simply doing the multiplication. That means you are applying rho J over A, which is equivalent to applying J gate over A. That means 0 gate, and which are result are stored in C. You are printing C, print C. Then what you are doing, you are applying row Z, that means applying Z gate over B. Okay, that means 1 gate. So, and you are storing the result in D. You are simply printing print C, printing the outcome, and you will see the magic. So, in first case, what you are doing, you are applying over it. So, it is 0 gate. A is 0 gate, 1 0. So, output will be 0 gate because Z gate applied over 0 gate is 0. 0 gate. So first output 1 0 means 0 gate. It is A. So there will be no change of sign. But whenever you are applying it over B, this was the gate 1. So the output sign will change. -1 gate. So this is how you see this is -1 gate. 0 -1. The sign has changed. -1. Okay. So always remember in case of 0 gate applied over whenever Z gate is applied over 0 gate, it will remain unchanged. But whenever it is applied over 1 gate, the sign will be changed. Okay. So this type of output you will experience there. So I am posting it in the comment box. Just run it. You will be able to see the required outcome. Just run it and let me know if you are able to run it successfully. Okay, very nice. It is already running. Okay. So I believe that all of you can run it. So we have seen the efficacy of X gate. We have seen the efficacy of Z gate. Okay, running, sir. Thank you very much, everyone. So now you will see the effectiveness of the Y gate, which is another single qubit quantum gate. Okay, that has another beauty. Okay, we will see the efficacy level of the Y gate. We have done it. We have done with the X and Z. Now we will see the Y gate, which is another important Pauli gate. So if you see, for example, Y gate, Pauli Y gate, so what will happen in case of the general structure? If what will happen that whenever you are applying the Pauli gate has this, Y gate has this structure like 0 minus I in the first one or I0 in the second row. So you are applying it over 0 gate. So it will give you outcome 0I format. Okay. And if you are applying it over 1 gate, it will give you the outcome in minus I0 form. Okay. So 0I and minus I0, depending upon how you are applying Y gate over 0 gate and 1 gate. Okay. So in a similar fashion, what we are doing, we are first of all installing Qt and then importing Qt. Okay, from Qt importing astral, then import numpy as np. We are defining 0 gate and 1 gate with the help of numpy array and assigning them under A and B. And then we are basically converting A and B into the Qt objects by the help of QAJ functions. Okay. And then what we are doing, we are simply assigning row underscore y with the help of sigma y function. Sigma y function will execute all the operations related to Y gate under the in the Python environment. So C equals to rho y into A, D equals to rho y into B, and then you are printing C and D. Okay, so and you will see the following outcome. So once you print there, what type of outcome you will get? You see, this will be 0 plus 0j, 0 plus 1 into j. Okay, that means this type of format, 0i format. 0 plus 0j means 0. 0 plus 1 into j means j. Okay, 0i format. Just a second, let me also. And you see, in the following case, once you are applying it over the Ket 1, what will be the output format? Output format is minus I0. Okay? What you are getting here? You will get it in case of the minus j format. 0 minus 1j means minus j. 0 plus 0j means 0. So the defined way of y gate applied over 0 gate and 1 gate, you will get the similar type of output. Okay, you just run it in your system and let me know. Okay, I'm just pasting the code in the comment box section. You just run it and you will get the desired outcome. Okay, once you are done, let me know. Okay, so all of you are getting the correct outcome. Very nice, very nice. Very good. Thank you very much. So always remember that you see we are doing the things in remote mode. Okay, so it's all about your cooperation to make it successful. So I am thankful to the organizers and thankful to all the active participants, those who have kept the patience and helped me to execute the session, because keeping the students of the first year and second year, I have started with very basic levels. We first explore with the classical gates. As I told you, that foundation should be very strong. Then you can do any complicated stuffs. So we first started with the classical gates, we executed examples of the linear algebra, and then we moved to explore on the single qubit gates, single qubit quantum gates, which was the prime focus of us today. So under that, we have explored X, Y, and Z gates successfully. Okay, I will share this particular notebook to all of you, and I will also share my YouTube channel link. There you can see all the advanced topic like quantum machine learning, quantum deep learning, quantum convolutional neural network. If you are interested, you can see there are some topics of the deep learning shared with you, how to utilize GPUs while exploring deep learning, how to for example, generative adversarial network. All those talks are there. So I will share my YouTube link with all of you. I mean, with the organizers, they will share with all of you. You can see, you can explore the channel. You can subscribe there. Even I can post it now in the comment box section as well, such that you can explore them. And if I get opportunity in near future, I will definitely cover a few more advanced topics. Okay. Always remember that basics should be very, very correct. So brush up your skills on linear algebra. Okay. So that will give you a lot of confidences. So what I am doing, I am just simply sharing the link of my YouTube channel. Just go there and subscribe it, and also explore the videos. You will be able to gain a lot of insight related to in the quantum domain, as well as if you are interested in AI domain. All the required videos are there. This is the link of my YouTube channel. Okay, I am also giving my phone number as well in case you want to stay connected with me. So this is my number as well, my YouTube channel link, my phone number, and my email ID. I am also giving in case anyone wants to communicate with me. Okay. So
Thank you, sir. Thank you very much, sir. So in case any participants have any doubt, then they can ask right now or they can type it in the chat box.
So it is already 8:30. So because you can see I am in my office, so I have to go back home. So I would request participants, if they kindly contact me personally or they can
Sure,
pass
sir.
the
Sure.
queries to the organizers, so they can also give
Sure, sir. Sure,
forward
sir.
those queries
That
to
will
me,
be.
because my email ID, phone numbers are shared with all of you.
Sure,
So
sir.
if you don't mind, I would like to leave because I have to go back home.
Thank you, sir. Thank you, sir,
So
for your wonderful insights. Thank you, sir. So I
mm,
hope all participants have enjoyed the session and have gained something from it.
yes, quantum bit flipping is also there. Okay, it is also there.
Right, sir.
Okay, so concepts. Okay, so who is in control? So can you get text in WhatsApp? I will discuss with you. Just drop me a text in WhatsApp. I will discuss with you, because we are running out of time. It's already 8:30, so I have to go back
Yes, sir.
home. So I am just in a hurry. Okay, okay. Just put the query in WhatsApp. This number is attached with WhatsApp. I will get back to you, because I have to explain. It will take some time. Okay, okay. Just get back to me in WhatsApp. So those who have the queries, this number, my 912330599, this number is available in WhatsApp also. You can call me, you can directly post the query in WhatsApp, I will get back to you. See, this is my number. I am again reposting it, okay?
Thank you, sir. So I hope,
This is my
sir.
number. I have also shared my YouTube channel link. Connect with me. I will
Yes, sir.
definitely cover. I would love to cover some advanced topic in the next session if I get the opportunity. And thank you very much to all the organizers. You guys are doing great job, because you see, it's the victory of all the participants that I have been able to complete the session quite peacefully, because it is their
Yes, sir.
active participation. Because you see, doing things remotely is not very easy. So it's required a lot of passion. So in sitting on Sunday evening, they have participated. That's the great job for them. And thank you very much to all the organizers. You guys are doing great job. So keep it up. My
Thank you,
best
sir.
wishes to all of you.
Thank you, sir. So I'm sure that, sir, that we will be needing such webinars, interactive webinars in near future, sir. I'm sure, sir. Thank you,
Okay.
sir.
Thank you. Thank you very much to all of you.
Sir,
Thanks for your patience. Take care.
so
Huh?
so
Yeah.
one more, sir, one more favor, sir. So could you please wait for 2 minutes more, and I would request everyone to
Sure,
switch
sure.
on their camera so that we can
Yes,
post
yes.
it on our
Have a
social
good
media
photo. Please
handles.
have a good photo. Okay. Sure, sure, sure. Sure.
So everyone, please turn on their cameras, as this will be posted in our social media handles. Wait, sir. Thank you, sir. Once again, thank you, sir,
Most
for
welcome.
taking
Thank
out
you. Thanks to all of you.
your
Thank you.
time from such a busy schedule, sir. Thank you, sir. Once again.
Thanks to all of you. All of you. Take care. Stay safe. Take care. Eh? Take care.
I would request all students to please stay, as we are going to organize our